Today's discussion is on lechateliers principle, and as we go into our final lesson on the first part of equilibrium, this is a good summary of what we've discussed so far. So when we talk about lechateliers principle, this is a way that is a good way to also to look at what Q does for us. So in lechateliers principle, it's just an application of Q. So according to lechateliers principle, when a stress is placed upon a system, such as a change in the temperature, if you change the pressure or concentration, then there's going to be what's called a shift in the position of the equilibrium to oppose that stress. We've learned that it doesn't matter where you start with equilibrium, that once a reaction reaches equilibrium, you always have that same ratio of products over reactants. And so again, it doesn't matter where you start. So if you add some reactant to it, well, now you've left equilibrium. And then again, that's going to cause Q, the Q value, all of a sudden, oh, we're not at equilibrium right now. Oh, then Q comes into play. When Q comes into play, then we have to decide which ways the reaction is going to proceed. With lechateliers principle, a lot of times we use the word shift. It really doesn't matter how you say it, whether you say the reaction is going to shift to the left or shift to the right, or proceed to the left or proceed to the right. It really just means the same thing. Okay, so this shift occurs when you change a chemical reaction, which again, we've already really talked about. When that happens, again, it will cause the Q value to change, and then the equilibrium will have to shift or will have to proceed in a different direction in order to bring Q back into numerical agreement with K. So let's go back for a little bit to the reaction. This is the Haber process, where nitrogen reacts with hydrogen to make ammonia. And the enthalpy change is a negative 92. We know that is an exothermic process. It releases heat. So here are three main things that you're going to see with lechateliers principle. Number one is you're going to add or remove some of the reactant or product. Okay, when this occurs, so let's say we've added some reactant. Let's say we've added some nitrogen. Okay, when this occurs, so if we add some nitrogen, the reaction is going to shift, or it's going to proceed to the opposite side of the chemical equation in order to use up the added reactant or product. Okay, and let's think about that in terms of Q. When we think of Q, Q is the concentration of NH3 squared, it should be a square bracket, concentration of N2 times the concentration of H2 cubed. Well, if you add some N, you add some nitrogen, then the concentration of nitrogen went up, which means that it was at equilibrium. But now that you've added some nitrogen, this value gets larger, which means the Q value gets smaller, which means that Q is now less than K. Well, if Q is less than K, we know again that the reaction is going to therefore proceed to the right. Okay, so again, anytime you talk about lechateliers principle, you can always use a Q explanation. Okay, another way you could describe this, you could talk about it in terms of Q. You could also just say that the addition of nitrogen causes the reaction to shift to the right, which means that the nitrogen is going to go down a little bit. Even though it went up, the hydrogen is going to go down and the products are going to go up. So the reaction is going to shift to, or it's going to proceed to the right. So when you add a reactant, the reaction is going to shift to the right, proceed to the right, and make more product according to lechateliers principle, and really according to Q. Okay, what if I added some NH3? If I added some NH3, now again, I've got more product, so the numerator just got bigger, the denominator stayed the same, and so now Q is greater than KQ, which means the reaction is going to proceed to the left, and it's going to make more reactant. And again, the amount of NH3 is going to go down. Now remember that the equilibrium value of KQ does not change. So even when you add some reactant or product, remember that the equilibrium constant does not change. Now the reason why that happens is because, let's look here at these three things. Let's look at nitrogen, hydrogen, and ammonia. Okay, let's say we're going to say this is the concentration, and that's N2. Okay, and let's say that right now I'm going to add some nitrogen to this system. Okay, so clearly the concentration of N2 is going to go straight up. I added some nitrogen. Okay, and then hydrogen, here's hydrogen, let's say, and again, just to make it easier, here's ammonia. Oops. NH3. Okay, so right now we've just added some nitrogen. Now, according to the lechateliers principle, this reaction is going to shift to the right. It's going to make more products. Okay, but remember, the equilibrium constant does not change. When you add or remove reactant or product, once it reestablishes equilibrium, the value of the equilibrium constant doesn't change. Well, how is that possible when all of a sudden, you've added a whole bunch of nitrogen? Doesn't that make the KEQ value change? Well, let's look at it. The value of nitrogen, we know that as the reaction shifts to the right, that the hydrogen value is going to go down. So again, let's put the K expression up here. We've got the concentration of NH3 squared over the concentration of N2 times the concentration of H2 cubed. So we know H2 is going to go down. So H2 goes down. We also know that ammonia, because it's shifting to the right, is actually going to go up. So ammonia is going to do that. So this one goes up. Well, wait a minute. In a fraction, if one number goes down, and if the denominator goes down and the numerator goes up, doesn't that mean that this number is going to get bigger? If those were the only two things, then absolutely yes. However, there is some nitrogen we have to consider as well, because the amount of nitrogen did go up, and the reaction is going to shift to the right. So once it goes up, what's it going to do as it shifts to the right? It's going to go back down. Okay, but you'll notice as it goes back down, it will never get down to as low as where it was before. It's still higher than where it started. So even though ammonia goes up a little bit, hydrogen goes down a little bit, nitrogen also overall is still going up, even though it's going to drop a little bit from adding it. Now, what that does is that basically cancels out those two, and so the equilibrium constant does not change. So the key that you need to understand here is that when you add a reactant or a product or remove a reactant or product, Q is going to change, and when Q does change, you have to consider, what does it take for Q to get back to the equilibrium constant? Does it need to proceed to the right, to proceed to the left, etc.? Okay, but again, the equilibrium constant does not change. Okay, so here, if some reactant or product is removed, the reaction is going to shift to the side where the substance was removed to reestablish equilibrium. So an example, using the equation above, if some hydrogen were added to this container, so if you added some hydrogen, the concentration of hydrogen would go up. The reaction is going to shift to the side to use up that additional hydrogen you've added, and the reaction is going to shift. So the amount of ammonia would go up, the amount of nitrogen would go down. So the amount of nitrogen in the container would decrease. If some ammonia is removed from the container, will the amount of nitrogen increase, decrease, or remain the same? So if NH3 goes down, the reaction is going to shift to that side to make more of it. And again, Q is a great way to describe why. Why does it shift to the right? Well, because as Q goes down, Q is less than K, and the reaction is going to proceed to the right to make more product to get back to the equilibrium constant. Okay, so if NH3 goes up, the nitrogen, well, the amount of nitrogen, it will decrease. Okay, situation 2. What happens if you change the volume of the container? And here's where it gets a little bit tricky, because when you change the volume of the container, if you change the volume, you're going to change the pressure. Okay, and many times on the AP test, they might say the pressure inside the container changes, but they don't tell you how it changes. If they don't, then you can't assume that the volume is changing. So if they ask you a question that looks like a lechateliers principle question, and they say the pressure inside the container is decreased, but they don't say how, then there's lots of ways you can change the pressure, not necessarily a volume change. So when the volume changes, which then causes the pressure to change, now the reaction, all of a sudden, let's say the volume gets smaller. Well, if the volume gets smaller, the reaction is going to shift to the side with fewer gas particles, okay, because it's got less room to move around. So when the volume is decreased, the pressure increases, and the reaction is going to shift to the side with fewer gas particles. Again, assuming we're in air, okay, we're assuming we're in a gaseous environment. What happens if you're in an aqueous environment? We'll talk about that in just a second. But in a gaseous environment, it's going to shift to the side with fewer gas particles. Okay, and again, when that happens, the equilibrium constant does not change. So KEQ stays the same. And that applies here, and it also applies here. Okay? So, looking at this example up here again with nitrogen and hydrogen and ammonia, if the volume gets smaller, the pressure is going to go up. If the pressure goes up, it's going to shift to the side with fewer gas particles. Well, here there's 4 gas particles. Here there's only 2. When the volume decreases, this reaction shifts to the right. And when it shifts to the right, it's going to make more ammonia. It's going to use up the nitrogen and hydrogen inside of that container. Okay, if the volume gets bigger, the pressure goes down, and then it's going to go to the side. It's going to shift to the side with more gas particles. It's got more room to move around. Okay, and remember, when you change the volume, that's changing the concentrations. And when you change the concentrations, obviously you're affecting the value of Q. So again, you can use the Q argument to talk about why this is shifting to the right or to the left. Okay, so if the volume of the container is increased, the pressure will decrease, and the reaction is going to shift to the side with more gas particles. Okay, now in an aqueous solution, we talked about this when we talked about the Q, what happens if you add water? Well, just like in situation 2 with gases, when the volume gets bigger, the gases have more room to move around. It switches to the side with more gas particles. When the volume gets smaller, it goes to the side. It shifts to the side with less gas particles. Okay, same thing with a solution. You add a bunch of water to a solution, all of a sudden your volume just got much, much bigger. Okay, and so this is our second way of describing when you add water to a solution, does the percent ionization go up, does it go down, etc. So if I looking at this reaction up here, if these were all aqueous instead of gases, which obviously they aren't, but if they were all aqueous and the volume got bigger, well, same thing's going to happen. It's going to shift to the side with more aqueous particles. So we come back over to this way. Okay? If you evaporate some of the water or you boil off some of the water, now the volume of your container got smaller, it's going to shift to the side with fewer aqueous particles, which in this case would be the right-hand side. Okay? So if water is added to a solution, the reaction will shift to counteract the water added by shifting to the side with more aqueous particles. Again, if water is evaporated or boiled off, the opposite's going to happen. It's going to shift to the side with fewer aqueous particles. Let's look at one of the questions we saw yesterday, okay, dealing with the BA-EDTA. When more water is added to the solution, it's as if the volume of the container has increased, which really it has. The amount of volume that the aqueous particles can move around in is bigger. And based on situation 2 above, when the volume of the container increases, the reaction shifts to the side with more particles. And since this is an aqueous reaction, the reaction is going to shift to the side with more, again, not gaseous, but with more aqueous particles, which again, looking at that equation from our assignment last night, that is the left side, which is, we had the Ba2 plus and the EDTA 4 minus separate. And then on the product side, we had the BA-EDTA, as we can see here, the 2 minus. Okay? So if it shifts to the side with more aqueous particles, that means that this is dissociating to make more of the Ba2 plus and the EDTA4 minus. And so as the solution is diluted, the percent of this that dissociates increases. So the percent ionization of BaEDTA increases, which causes the number of moles of barium ions to increase. Okay. Situation 1, when you add reactant, add product, remove reactant, remove product, the equilibrium constant does not change. Okay. Situation number 2, when you change the volume of a gas or change the volume of a solution, the equilibrium constant does not change. Okay. Situation number 3 is a temperature change. Okay. The temperature change at which the reaction occurs changes is the only time that the equilibrium constant actually changes. If you change the temperature, you change the equilibrium constant. Other than that, it does not have, the equilibrium constant does not change. Okay, removing or adding reactants or products, compressing or increasing a container causes shifts to occur, but the equilibrium constant itself will not change. When the temperature of the reaction changes, though, the reaction will shift to counteract the temperature change, and the equilibrium constant will also change. Okay, how the reaction shifts, though, depends on whether the reaction is exothermic or endothermic. So coming back up here, because this reaction here has a negative delta H, we know it's an exothermic process, and that's going to be important here in just a second. Okay, so for example, in the equation above, delta H is a negative value indicating an exothermic reaction. Heat is being released. Since heat is being released, we can treat that reaction as if heat were a product because it's being released from the reaction. So when you have a delta H that is negative, you treat heat as if it were a product. Okay, well, now let's think about it. If heat's a product and I raise the temperature, what have I done to the amount of heat? I've added some heat. It's like I've added a product. And what does the reaction do when you add a product? It shifts to use that added stuff up, so it's going to shift to the left. So when it's exothermic and you raise the temperature, it's as if you've added some product, and the reaction is going to shift to the left, decrease the amount of ammonia, increasing the amount of nitrogen and hydrogen. Okay, if it's exothermic, like this one still is, and you lower the temperature, it's just like you've removed some NH3. You remove some heat, it's going to counteract that by making more of it, and the reaction is going to shift to the right. And again, when it does that, the amount of nitrogen and hydrogen is going to go down, the amount of ammonia is going to go up. Okay? Now, what if it were endothermic? If it's endothermic, then obviously delta H is a positive value. And if it's positive, where do we put heat? It's taking heat in. It needs heat for that reaction. And so we put heat as a reactant. And then again, same principle applies. If the temperature goes up, what does the reaction do? It shifts to the right to counteract that added heat. Okay, if we lower the temperature, we've removed some heat, the reaction is going to shift to the left to make more of it. Okay, so now we just treat the equation if we were adding or removing a reactant or product. So you just have to figure out what side does the heat go on. If it's exothermic, it goes on the product side. If it's endothermic, it goes on the reactant side. This is going to cause the equilibrium constant value, again, depending on what you do. But if we raise the temperature of the above a reaction, the reaction is going to shift to the left, and that's going to cause the equilibrium constant value to decrease. So anytime they ask you a question about, the equilibrium constant going up, the equilibrium constant going down, okay, usually it's going to involve something to do with temperature, because that's the one thing that causes K to change. Okay, if the temperature of that reaction above is lowered, the reaction again is going to shift to the right to create more heat, causing K to increase. Okay, and likewise, endothermic, we treat heat as a reactant, and then again, those same principles apply like we just discussed. Okay, now, what are some other things they're going to do to try to trick you with lechateliers' principle? Okay, if they add a chemical that's not part of the chemical reaction, and it can be close, it can be really, really close. You could add, for example, for the Haber process here, you could add some H2O. Well, H2O is not part of this reaction. H2 is. They could add some NH4 plus, which again, close, but that's not NH3. It has to be the exact same thing. If you add some N2 gas, that is going to cause a shift to occur. If you add nitrogen atoms, just N, that's not going to cause a shift to occur. Okay, so if you add a chemical that is not an exact part of that chemical reaction, so if any gas that is not involved in the equilibrium is added to the container, the total pressure is going to increase, right? You add more gas, the pressure is going to go up. Okay, argon, very reactive gas, commonly used like this. Okay, but we haven't decreased the volume or increased the volume. Okay, so in that case, it does not affect the partial pressures of the gases, because remember the kinetic molecular theory, gases don't take up any space, even though they actually kind of do. Okay, so it doesn't affect the pressure of the other gases, and it does not cause a shift in the equilibrium. Okay, only by increasing or decreasing the volume will it cause a pressure change that will cause the equilibrium to shift. So adding a gas that's not directly involved in it will not cause it to happen. Okay, number two, if you add a catalyst. Okay, a catalyst, as we know, makes a reaction go faster by lowering the activation energy. It does not affect delta G, we learned. Okay, but it does, so it causes the activation energy to be lower, and it does cause the rate of the forward and reverse reaction to go up, and it increases the rate at which equilibrium is achieved. You get to equilibrium faster with a catalyst, but again, it does not change the composition of the equilibrium mixture, and therefore does not cause a shift to occur. All right, so let's look at some examples here. And there's a good example here, an example too. We'll see here in just a second. In which direction will the equilibrium shift when each of the following changes is made? So first of all, right away, I see the enthalpy change as being positive. So what I'm going to do is I'm going to write heat over here on the reactant side. Whenever I see a positive delta H, just write heat as a reactant. If it's negative, write heat as a product. Okay, in which direction will the equilibrium shift when each of the following changes is made? If I add some N2O4, I've increased the amount of N2O4. The reaction is going to shift to the right to counteract that. So this is going to be a shift to the right. Okay, if I remove some NO2, so this goes down, the reaction is also going to shift in that direction to the right to make more of it. So that is also a shift to the right. Okay, so the concentration of N2O4 is going to go down. Okay, if I increase the total pressure by adding some nitrogen, okay, N2 is not directly involved in this reaction. So if that's a gas or anything that's not directly involved in the reaction, that is not going to cause a shift to occur. So no shift there. If I increase the volume, the pressure is going to go down. If the pressure goes down, it's going to shift to the side with more gas particles. It's got more space to move around, so that is a shift to the right. What if both gases, what if you have this exact same number of gas particles on both sides? If that happens, that's okay, but when you change the volume, what's going to happen? Nothing. Okay, if you have 4 and 4 on both sides, you're not going to have a shift that occurs at all. Okay, if I decrease the temperature, so now again, let's put our heat back up here. So if I decrease the temperature, I'm removing some heat from the reaction, and that the reaction is going to counteract that by shifting to the left, and it's going to create more heat, and so that is a shift to the left. Okay, use the following balance equation to answer this question. So U3O8 with U3O8, which is a solid, reacts with Cl2 gas. So we know in the equilibrium system, If you add some solid, it's not part of the equilibrium system, or you remove some solid, it's not going to cause a shift to occur. However, if a shift does occur, then, for example, if this reaction shifts to the left, the amount of U3O8 is going to go up. So let me clarify that here. If the amount of a solid changes, it does not cause a shift to occur. But if the amount of Cl2, O2, if a shift does happen, and it shifts to the right or shifts back to the left, it doesn't matter. If that does happen, then the amount of U3O8 does change. So a solid doesn't make a shift occur, but if a shift does occur, then U3O8, the solid or the liquid, would be affected. So let's use that knowledge to look at these two questions. After a certain period of time, a mole of O2 is added to the mixture in the flask. So we're going to increase the amount of O2. Does the mass of U3O8 in the flask increase, decrease, or remain the same? Okay, so the reaction's going to, because we've added some O2, it's going to proceed or shift to the left, and so the amount of U3O8 is going to go up. Okay, now how would I justify that on the AP test? I would say basically that. First of all, I would say increase, because I'm answering the question. I'd say an increase in the amount of O2 causes a lechateliers principle shift to the left, and that causes the amount of the reactants to increase. And that's really all you would have to say. Okay, and then in a separate experiment, 1 mole of U3O8 is added to the container. Does the mass of O2 increase, decrease, or remain the same? So again, now we've added some solid. Again, when you do that, because it is not part of the equilibrium constant expression, it does not cause a shift to occur. And again, that's how I would say it. The mass of O2 would remain the same because U3O8 is a solid. A lechateliers principle shift does not occur, and O2 will remain the same. Okay, and I believe, yep, that is it for lechateliers principle.